So good afternoon, everyone. Apologies for the slight delay in this session. So welcome to the session which is called the virtual modeling of batteries. So if you were wondering why is it this topic important for us at the European Commission and at CINEA in particular, so as you all know, the virtual modeling of batteries is an important activity, so it is expected to reduce the development time and costs of the batteries. It also optimizes the overall design and the production processes by reducing the number of experiments that are needed for the development of batteries, as this development is often using timely and costly trial and error methods. And also the virtual modeling also helps to reduce the overall research and innovation costs. Thanks to virtual modeling, we also have a better understanding of the performance of the batteries, which allows us to inform the end users on the optimal usage profiles for minimum capacity and degradation loss, and also supports manufacturers to closely manage the performance of battery cells. And in that sense, so virtual modeling is indeed fully in line with two of Commission priorities, notably in terms of digitalization and the greening of our economies, as it allows the batteries to stay in function for longer and also moving away from fossil fuel economy. So in this session, you will learn a bit more about the accomplishment of the two of the projects that we have financed, and also about the impressive knowledge that they have built in both in modeling and also in virtualization with support from Horizon 2020 program. So it is my pleasure to introduce you the speakers of today. You have noticed as well, I also have next to me Mr. Paul Schiffbaenker from AVL LIST, who is a mechanical engineer and business economist. He specialized in product development, in project management and innovation management in the field of automotive and solar industry, in particular in battery verification and validation. And Mr. Schiffbaenker will help me also in the question and answer session that will be in the second part of the presentation today. And the two speakers next to me, so first Dr. Elisabete Ayerbe from CIDETEC, who is the coordinator of the DEFACTO project. She has more than 15 years of experience in batteries, fuel cells, and related technologies. She's a very experienced project manager for a lot of Horizon 2020 and Horizon Europe projects. So we are very pleased to have you today and learn more about the results of the DEFACTO project. And last but not least, we also have with us Dr. Martin Petit from AFP Énergie Nouvelle, who is the coordinator of the Modali Square project. Mr. Petit is contributing to the development of electrical storage systems for system simulations in automotive applications in IFPEN. And some of you might remember Mr. Petit's intervention from last year. I think it was on the same stage. So we are very much looking forward to hear from you, Mr. Petit, about the advancements that you had in terms of measurements and material characterization since last year. So I will give the floor to my colleagues just to recall. So each of you would have 15 minutes for your presentation. And for the audience, so you would have the chance to ask any urgent questions on the presentation just afterwards. Otherwise, we have a more dedicated question and answer sessions with my colleagues as well. So, Mrs. Ayerbe, I give you the floor. Yep, thank you.
Alexandru, for your nice words. And thank you, the organization, for giving us the opportunity to be here, explaining the DEFACTO outcome. So DEFACTO stands for battery manufacturing optimization through multiphysics modeling, and it was started in 2020, was over last December. So we were 4 years running the project, trying to answer all the KPIs that were included in the LCBAT 6 topic, that were a lot of challenging KPIs. So, which is the overall picture of the project or project concept? Let me start with the left-hand side picture, and this is the main purpose of the project, and we have a clear idea of we build models for certain purpose, and the purpose is clear. We need to accelerate the development because in the end we need a cell that goes into the battery pack that will go into the larger scale at the whatever system might be. So we need to contribute on that field on the development side, and for that we need to have much more understanding, because we need to somehow reduce the experimental workflow, or at least avoid the certain activities on the trial error approach. So the main purpose was this building the baseline on multiphysics modeling tools, and very much dedicated to electrode fabrication, electrolyte filling process, and then linking this to a specific process chain into the cell performance and cell aging. So at the center, let me see if I'm able to, where is the sorry, yeah. So the main purpose, as I was saying, is the building the multiphysics, multi-scale modeling on the electrode fabrication and electrolyte filling. And for that, we carry out a lot of activities in setting up the baseline, but we cannot forget that we are in a real area as well, and we need to have a lot of insights and a lot of information from the real cells, real materials, and real electrodes. So they were like a combining modeling effort. There were certain activities on the characterization, manufacturing, and without forgetting certain aspects on the standardization. So the clear picture was, the picture was clear. We needed to build this baseline and to answer certain KPIs, and these KPIs were very much dedicated to increase the energy density, increase the cycle life, and obviously reduce the cost. And also certain activities on reducing the experimental workflow. So for that, obviously, we are, CIDETEC is the coordinator of the project, but we are not alone in this. We've been working a lot with many partners in the consortium, and altogether we were 12 partners, so CINEA, CERT, DLR, UPM, Fraunhofer, UNE, IRITAR, ABE, Leclanché, TU Braunschweig, and Sustainable were building this huge consortium with this specific target of building these physics-based models, with this picture of having more insights on the electrofabrication, electrolyte filling, and linking these two processes into the cell aging. So as I was saying, the project was started in January 2020 and was over last December. We had a total funding of 6 million euros, and it was answering the topic LCBAT 6. Yeah, so I like to include this slide, which somehow summarizes all the achievements and somehow So let me start from the beginning, because I was saying that the main purpose obviously was to set up the baseline. So we developed 12 modeling tools, very much dedicated with this specific electrode fabrication, electrolyte filling, and then addressing certain aspects of the aging. Then, obviously, main purpose of having these tools were to give an answer to optimization, somehow reducing the, as I was saying, the experimental workflow. So going straight to the point, so identifying the main limitation on the cell level, or electrofabrication or whatever. So having this information beforehand, then you can save a lot of time in the experimental workflow. So, and for that, we needed to carry out a lot of work on the experimental side as well as in the manufacturing. So we built around 130 cells, not only dedicated to one specific chemistry, because we were navigated along the Gen 3A together with Gen 3B technologies, addressing the challenges for each particular chemistry. And then also, as we carry out aging to these cells, or at least most of the cells, and then we needed to also understand a little bit on the degradation mechanism. So we carry out post-mortem analysis, and then we link to certain electrochemical characterization and dedicated much to identify the degradation modes. Then we were able to have information for model validation. So we have, in the end, carry out the activities on these models calibration for 2 specific chemistry, and they were graphite NMC 622, graphite silicon NMC 811, and then we were taking this into consideration all along this way with the information from the optimization tool, with the information from the postmortem analysis. We were somehow able to guide this time space of the electrofabrication and the cell configuration. So this is main aspects on this specific, main achievements with this specific project, but then we also carry out certain activities on the standardization, because when you are dealing with the modeling or even with the experimental side, you need to carry out, and you want to compare, my model is better than yours, or your experimental cell it has a lot of better performance than mine. We need to standardize the way we build this test, for instance, or the way we validate the models. And we had this idea of somehow contributed on this line as well. So we carry out certain activities there. And then we were able to do certain work for the academia, publishing results, but as well as open source, because we were able to release certain open source that are already available in the DEFACTO webpage, in which anyone can download, play with it, run simulation, and then give us feedback, because this is the purpose of having this open source available. So results, which is the most important thing today, I guess, sharing real results. Yeah, so this is all the workflow for the manufacturing models, and as I was saying, we are very much dedicated to electrode fabrication and electrolyte filling. So in here we were the first three models were very much dedicated to the electrode fabrication, while then there is this column related to the filling process. So I'm now focusing on electrode fabrication, and we were focusing on the mixing, drying, and calendaring. And then from this approach that were developed by a partner, and it's a DEM approach combined with the fluidynamics software, we're able to somehow identify which are the best parameters for achieving certain properties. So for instance, in the disperse or mixing process, they were able to predict certain rheology properties depending on the agglomeration of the carbon black domain. In the drying step, they were able to predict properties so relevant in electrodes, such as the porosity and tortuosity, depending on a specific process parameters of the drying. And in the calendaring, again, depending on the pressure that it's implied in this specific process, they were able to predict, again, porosity and tortuosity, so that they could also predict ionic resistance, which is very much interested to know in advance in order to see if there will be a certain limitation, for instance, in fast or high C rates. So this is, as I was saying, these are the three models that were developed on the electrofabrication, and then on the filling scale, we were tackling this step from the multi-scale approach. So they were developed lattice-Boltzmann process scheme, also Pond network modeling, and then also Richards equations, and then basically because we want to understand properly how to avoid the gas entrapment in the cell itself, because this gas entrapment, for instance, can reduce the lifetime. So you need to know in advance which are the best parameters of the filling, so that, for instance, taking into account that the nanopores of the binders will be crucial again to address this issue, or the pores all along the active material, or the way or in which sense or in which flow you inject the electrolyte will have a lot of impact again on these specific cell performance properties. So yeah, and then this is on the manufacturing step, but we did some work also on data treatment, and considering the data that was obtained through the characterization workflow on the microstructure, they built a library, software library, that they were able to predict certain microstructure. And this is really important, because then you can build like microstructure that has not even manufactured, and then link directly to the models that are dealing with this microstructure building through the electrofabrication. So, and then now dealing with the performance, again, with this multi-scale approach, we go from atomistic to meso to the continuous scale. And in particular in the DEFACTO, we have this graphite silicon, and here it's really important, the swelling of the silicon. And this swelling, you need to you need to address correctly this swelling, because otherwise it might cause certain cracking. And then also this cracking then will lead to lower or higher polarizations, and then also lower cycle life. So basically, we were talking from this multi-scale approach, predicting on the atomistic scale certain properties of on the mechanical side, and giving this information on the electro modeling, and then it turns to the battery cell, where you somehow homogenize the information at the cell level, and then you can predict certain aspects of the whole cell. Yeah, so, oh, sorry. I don't know what happened. I don't know what I did.
I also don't know.
Sorry.
The help of the technician. What did you?
I did.
Resume slideshow. Should be fine.
Okay. Okay, and then I was talking about these certain aspects that not really in the topic itself, but we think it's really interesting, because it's not only about building an accurate model, it's that you need to run in a certain reasonable time, so that you don't need to wait like a couple of days or weeks to see the results. So we were also addressing the computational cost, and this is why we were working very much on the reduced models. So basically, this is not a simplification of the model, it's just that we play with the numerics, and then we capturing all the mechanics and all the physics and all the electrochemists without simplifying equations. We were able to reduce the computational time by a factor of 10. So this was very much interesting, and also something that I didn't mention, but this is already available in the DEFACTO project, so you can run simulations within this tool, and this is, I think, another outcome of the project, which is good because it's good for the community, where you share these kind of achievements, and then someone can take advantage of this. So this was on the reduced models. So, but then, and this is very much on the design space, but we were thinking that maybe with similar approach, we were able to think in a way that these tools can be also used for control aspects. So we built proof of concept, I would say, but it's already available again in the GitHub of CINEA. So we implement physics-informed neural networks in order to have a very fast model. So basically, it's a neural network model, but with information on the physics. And here is the comparison between the single particle models solved by finite element or this PINS model. And this is again it's available in the web page of the DEFACTO. And yeah, so this is another achievement in which we have made. And then very much on the optimization. So, and it's as in the DEFACTO, where the main purpose was to somehow save the time and improve the design. So we needed to address the optimization tool. And here, I mean, this is what we were trying to build with this optimization, but this implies that the reduced of the model that was developed needs to capture the parameter dependency and also the time dependency. So there was a lot of work in here, but with this focus on having a model available. And again, it's available. So manufacturing, this is all the cells that were manufactured. And yeah, we aged them so we properly made a design of experiments. So because in a way that we were identifying a specific degradation modes for each of the experiments, and we carry out cycling as well as calendar. And then we did postmortem. So we were able to identify the degradation modes, and this is really relevant for model validation. And we, together with the cycling data, through the QDB analysis, we were able to evaluate the lithium cyclable loss, quantify lithium cyclable loss or active material loss, in which we have used the data for model validation. Yeah. So, this is an example of model validation for the two chemistries. So, and we've been working very much on this graphite NMC622, which were the cells that were built and manufactured at the beginning. So we were able to validate each of the models for each of the steps in the whole value chain, as well as we did certain work for validation in this specific chemistry. So these are the samples we've been tackling. And then I wanted to address that we also wanted to somehow start communicating each of the steps with the next one. So I mean that, for instance, drying step might have an impact on the microstructure, but then depending on this microstructure will also affect the calendering step, as well as the final microstructure will affect very much the way you include the electrolyte. So quick coupling, it was also necessary, and even though it was really not written in the grant agreement, we thought it was really interesting to collaborate within the different models. So these are some of the samples. So here what they are doing is they are capturing the calendering parameters, influence on the microstructure of the electrode, and then with the mesoscale modeling on the cell performance, they were able to predict the ionic resistance or ionic contribution, as well as of electronic resistance. So this is, for instance, one way to link electrofabrication together with performance. And if you know in advance this information, then you don't need, for instance, start modifying the additive conductive, because maybe the limitation comes from the ionic resistance and not on the electronic resistance. So this was one of the samples. Another one, it was on the wetting behavior. So with this multi-scale approach, we were able to predict certain pressure saturation plots. And this is again crucial, because if you want to avoid any gas entrapment, and you need to optimize and obviously accelerate the electrolyte filling, you need to know in advance this kind of plot, because otherwise maybe you don't reach the full minimization of the gas entrapment. So yeah, and then again multi-scale approach, which is again very interesting, because you are not only addressing the electrode at homogenized level, because obviously the microstructure is huge, very complicated system, and it might depend a lot on the fabrication, and this microstructure will depend very much on, as I was saying, on the fabrication step, but will have a lot of impact on the performance. So the way you manufacture this microstructure, the way you will get the final results. So this is another sample in which we are combining this multi-scale approach, and together with, for instance, in the calendering steps, the pressure that were the roles suggested. Yeah, and then obviously I was saying that we solved this optimization, and in here this optimization gives us a lot of information, for instance, which are the crucial, because it was also implying certain sensitivity analysis, and we didn't need to know exactly which was the most sensitive parameters that were affecting on the cell performance, and what we in the end discovered that we were able to achieve high energy density, that, by the way, in the cold test was requested to achieve 300 watt-hour/kilogram, which is, I guess, a huge number. So we did this work as well, and this is good for us, because you know exactly which are the parameters that are more affecting, and which are the ones you need to modify. Because if you are not modifying these ones and you are modifying other ones, you won't get the results. Okay, and finally, standardization. So it's again on the modeling. We are covering a lot of models. This needs to have a lot of information on the parameters, because in the end we need to have models that are validated against real cells. But so you need to have the information on which are the parameters, you need to have in the information in advance, but also the way these parameters are measured, because what we've been seeing, and I didn't put anything on there, but the way you measure porosity, for instance, is crucial. So you can have like theoretical value, the porosimeter value, or other techniques, and depending on the technique and the procedure, exactly, you won't have exactly the same value. So something, I mean, this was a starting point, and this was obviously not a standard, but it's a CINEA version agreement, so it's like a certain baseline to on that road of standardization, and yeah, we are somehow proud of it, because in the end it was published, these two CINEA version agreement. Yeah, and something on the publication, that at this stage we have achieved 13 publications, and again, we are happy because, yeah, at a certain point, this is a way to share results with the community, and yeah, we think it's also important to have this openness to the community. Yeah, mid-long term expected impacts for the project is not really an easy aspect, but what we can say is that one of the aspects in which we were very much focusing is to build these accurate models, and not only accurate because we wanted to have very efficient models, not to wait a long time for the simulation. Yeah, we were able to guide on also enhancing lifetime, because the models were already included. We were including the degradation modes and degradation mechanisms. So with these different paths and also with different testing procedures, you can somehow predict the lifetime of these models. And then, as we have the capability, then link to the fabrication as well. So yeah, certain activities on these learning and training methods that were available for anyone that could be interested, that are already available in the web page. Yeah, so, and this was a really challenging target, but we've been doing certain work on making calculation on how much effort does it take us internally to manufacture a prototype cells. And then what we did also in the parallel is having this information in advance, how much time can we save. So we can say now that we are not on the 30%, but we can say that we are on that way, because obviously you save time knowing what is the real problem, and these models somehow contribute on that direction. Yeah, and certain aspects on the societal requirements and demands, basically because having the information, the manufacturing processes in advance, you can save again scrap rate in a way that maybe knowing in advance the parameters you need to fabricate your electrode, you don't need to make some trials, and this is on that level of achievement. And then finally, yes, I was saying the standardization activities that were carried out, that obviously it didn't turn into a real standard, but it's on that level. All in all, so what we can say is that, yeah, we have simulation platform in which you can replicate electrofabrication, electrolyte filling, and then again, cell performance, somehow linking. So we were able to show that these models can contribute to generate more insights and then go straight forward to the specific items. So, and then all in all, this is like a baseline, a foundation for the models that could be somehow used for future digital twins in any kind of industry level, pilot line level, or whatever. Obviously, we are very far from building these digital twins because these models were pretty much built for addressing the understanding, not really for controlling the manufacturing, but yeah, they could be used like a baseline for this specific purpose. So, and that's all from my side. I would like again thank you to everybody, to the audience, and also organization for giving us the opportunity to be here on behalf of the whole consortium. Yeah.
Thank you very much, Elizabeth. So is there any pressing question on the presentation or clarifications? If not, then we will move on to Mr. Petit. So please, the floor is yours.
Thank you very much for giving me the opportunity to present the Moderators project for, I think, last time today, because as for DEFACTO, we are reaching the end of this project. We finished it in August this year. So to present this project, it's also a project from the college CIBAT 6 that was in 2019. So we thought about this project a long time ago now. We formed this consortium regrouping partners from the academics, also from the industry, with cell manufacturer, material providers, software providers, in order to achieve the main objective of the project, which were to develop new simulation tool chain, able to tackle the new behavior of next generation batteries, especially the generation 3B with a high content of silicon and generation 4 with solid electrolytes. So when we thought about this project, we had in the consortium, as I said, metal manufacturers, and they wanted to have information on how they can provide materials that are fit for purpose for next generation batteries. And when they invent or create a new material, how can they say to battery manufacturers or OEM that my material is better than what you have now, and you can increase your performance thanks to my material. On the same way, battery manufacturers will have these materials, and how can they optimize the implementation of this material into new batteries in order to get better performance in terms of power, energy densities, and also safety and aging. And finally, at the end of the line, end users and OEM want to use this battery in order to get electrified vehicles, so all electrified devices that are able to meet with customers' demands, and especially in terms of performances regarding power and energy density for a larger range and better performances. So as you know, we are looking for new materials, new chemistries. When we thought of this project, obviously we were very optimistic, saying that in 2025 we will have solid-state batteries in all of the cars and so on. Obviously we are not there yet, but we needed to have these tools in order to understand how they work and what needed to be done in order to address the main difficulties. Especially, we thought that there was a very strong focus to be made on mechanics on this subject, because we have new behavior that we see relating to mechanics and coupling with electrochemistry, leading to higher degradation, higher difficulties and challenges for implementation into new cells. So that's why that was true for silicon-based anodes, but it's also true for the solid-state electrolytes. And obviously, we did not want to do that just for fun and having something that is not validated. We wanted to have a validation that was fit for purpose and oriented to the end users. So we asked to the material manufacturers, battery manufacturers, and OEM, what kind of validation do you need for these models in order for you to make sure that they are fit for purpose for your utilization in the end. So that was also the objective of the Moderators project. So the main results that we have are obviously two modeling tool chains. The first one was dedicated to Gen 3B cells, where we developed a multi-scale approach from molecular modeling until full cell behavior. So from there, this tool chain was tackling a lot of different aspects, but we needed experimental results in order to validate it. So first, we needed to have an experimental characterization of Gen 3B battery behavior. So as you maybe have seen in the LCBAT 5 presentation this morning, yesterday, it was not an easy task to get these cells working, because we have very challenging materials to implement into the cells. So we had to manufacture cells which were provided by SAFT. We had 45 cells, 5 ampere-hour cells, with 20% of silicon in the negative. So that's a very big amount of silicon, leading to a lot of issues regarding the cycling of the cells. But nevertheless, we were able to create these cells and analyze them in order to get their general performances, the mechanical behavior of the electrode and the full cell, in order to understand the behavior of these systems, and also the main aging that are impacting the aging. To do that, we needed to put together an experimental campaign and share these results all together. So to do that, we needed to do a benchmarking of the laboratory practices in order to make sure that we had the similar results and we could compare these results all together. And then put some protocols in order to share the results between the partners. What we saw was very interesting results regarding the aging, with a strong impact of mechanics on the aging of batteries. Obviously, the more the battery swells, the worse it will behave in terms of durability. And we saw that with some conditions, we had a very fast capacity degradation. And also, we were able to see some very specific behavior regarding the swelling due to the intercalation, the differentiated integration of graphite and silicon. So it was very interesting to see that and to see how the model compares to this kind of behavior, to see whether we were able to tackle this specific behavior. On the modeling side, so it was, I'd say, very easy, much more easy to do this modeling compared to the experimental. Modeling, you just have to run the calculation and you have results. Obviously, you cannot say the results are true before you have the experiments, but you have results at least. It's not the case already for experiments. But the thing that we were very lucky at is that when we compared the experimental results at the end of the project with the modeling results from the beginning of the project, they were matching quite well. So we didn't have to have a lot of iterations in order to make this validated and calibrated. So from the molecular level, we developed some specific models in order to understand the transport behavior and mechanical behavior of the materials. These parameters were used then into a particle scale model, which is here, where we could understand how the particles made of silicon and graphite would swell because of intercalation and alloying. This gave us some specific behavior of the particles that could be implemented into an electrode level model, where we could understand how the electrode will behave during the cycling. And this was integrated into nominal behavior, including safety, for the full cell and 3D cell behavior in order to understand the heterogeneity effect on the battery behavior. The same kind of approach was also done for Gen 4 batteries with solid-state electrolyte. So we had to prepare specific cells for this kind of material, and it was already a challenge for Gen 3B, but for Gen 4, we had an even lower TRL, so we had a lot of surprises depending, linked to the behavior of the cells compared to what we expected 5 years ago. We were able to build 20 cells in pressure cells with lithium indium and the negative NMC 811 and argyrodite electrolyte, and we did the characterization. The first aging campaign we did was not so successful with a lot of difficulties, so we needed to discuss it from the modeling point of view to say, okay, we observe that, what can we understand from the modeling, and how can we improve our experiments in order to get some results, at least to validate our models. We did some specific material characterization with NMR, SEM, and so on, microstructure characterization, and a full cell characterization to evaluate the C rate and the capacity of the cells. The TRL was too low, sadly, to do some aging on this subject because after a few cycles, the cell would not have any capacity left. So we had to stick with nominal behavior first. On the modeling side, we did also some molecular and ab initio modeling in order to understand the behavior of the electrolyte, how the lithium ions are transported into the electrolyte in order to put them into a full-scale model. What are the properties of the lithium indium, which was not the main topic in the beginning of the project, and also what are the main properties of the interfaces. Interfaces between NMC and argyrodite, and interfaces between argyrodite and lithium indium, and argyrodite and lithium, which showed some obvious result at the end, but it was possible through calculation to validate what was observed in real life, that especially that lithium indium was far more stable compared to lithium towards argyrodite. Then we did a phase field model in order to evaluate the behavior of the electrolyte and how it was stable in terms of lithium argyrodite interfaces. So we were able to build this model in order to evaluate the dendritic growth into this material. We went to microstructure modeling in order to evaluate the effect of the microstructure on the positive electrode behavior with the NMC. So it showed that due to swelling and of the NMC and mechanical stress, we had a very fast degradation of the interfaces at the NMC side, leading to material capacity fade for the cells. And finally, at the full cell level, we were able to validate the model behavior in 1D on the full cell behavior in order to finalize this model at the end of the project. So what are the main impacts of the project? First, we dedicated this work to next generation batteries. And this gives us a lot of insight on this behavior and how to implement new materials and new technologies for the next generations. These new models have been implemented now into industrial tools from Siemens. These commercial tools are now available for customers in order to create new designs and create new implementation for these cells. So you have two examples. This first one is for StarCCM+, when you have a battery design tool that is able to replicate push cells in 3D in order to evaluate the behavior of the full cell. And on the right, SimCenter AmSim, when you can evaluate the cell behavior into a full system. Then we were able also to evaluate the reduced development times of these models thanks to the developments. So it was not an easy task because of the low TRL. A lot of things that we had to do was to reinvent the wheel as we were doing the work, obviously. But when we compared what we did from the third generation of cells for J3B and the second generation of cells, we saw that we were able to reduce for 35% the number of experiments needed for this specific approach. Finally, this is obviously similar to what was presented by Elisabeth in DEFACTO. It's the beginning of what we need to do in terms of modeling. We spent a lot of time in this project in order to develop cells, which was not the core of the project. We needed to develop new models, but we needed also to validate them. When we are working on new projects now, we need to reinvent some part of this work, but thanks to Modelis project, we have at least some historical framework that can be used in order to implement new particularities to this framework. I tried also to count on how many models we developed. So at least 12 models were developed regarding aging, tools for blend modeling, reconstruction of performances, ab initio models, particle scale models, electrode scale models. And these are now available in industrial softwares in order to use them further. We have 4 papers published since last week, and we had a lot of presentation in conferences and workshops. And then this work can be used in further work in other European projects and national and regional projects. As I said, modeling is just a central initial part, and we can use these new models in order to better integrate these batteries into full systems, to create better design, as was presented by Elisabeth from DEFACTO, to improve manufacturing by using the outcome of this model in order to understand the effect of manufacturing on the performance of the cells, and also to improve experiments in order to reduce the number of experiments needed for testing. So I'd like to thank the European Commission for funding this project, and to thank all the partners of this project for their work and their dedication to this subject. And thank you for your attention.
Thank you very much, Martin. So if there are any questions for either Martin or both Martin and Elisabeth, please go ahead.
So if there are no immediate question from the audience, thank you also from my side, very interesting presentations. Since both projects were ending recently, I'm of course interested how the results are now applied. Martin, you showed that Siemens is having a commercial approach, bringing that into their systems or into their simulation tools, StarCCM. Elisabetta, you have an open source approach in your project. How is this accepted by the community, by the non-consortium members? I hope that the consortium members use the models since they developed them. Can you rate how this is now spreading into the industry, the models that were developed?
Yeah, so within the DEFACTO, we didn't have any software industry on board. And then what we thought it was also really interesting for the community itself to share these results. So we got these final results, and now everybody can use them. I know that it's not really easy to have dissemination of these kind of tools, because you normally disseminate results showing numbers that I've been achieving certain cells with certain KPIs, but it's true that we didn't work much spreading all this information into the huge community. So we now, even though the project is ended, we are in a phase that maybe we should be somehow publishing or making more dissemination activities on that level, even though the project is over. But because we are really convinced that the tools could be used, and obviously once you share this open source, anyone can improve them. And it doesn't make sense to start from scratch if there is something already built. So and then regarding your question on the industry, I think we honestly, I'm being completely honest, we didn't have the opportunity still to access to the industry needs. So we know the industry is working in this field, they are very much interested, but within the DEFACTO, we were pretty much focusing on the development and running a lot. You are somehow sorting a lot of difficulties on the model level. So and then we got these final results. We are pretty convinced that it's really interesting, but still I need to admit that we believe we didn't succeed on that level. So
Well, the models are open source available on your homepage, so I think that's the models are openly available on the homepage, so maybe that's a good way to spread the news. First step today.
Yeah, for Modalists, obviously we had a partner, two partners actually in the project. You had Torino also as a commercial software that were developed during the project, and Siemens have two softwares. And it was also a driver for us because they have specific teams in order to listen to the industry needs and try to answer to these demands. So they are not open in the end because they are selling it, but they have a very wide penetration into the industry. A lot of people are using Siemens softwares for their developments. Battery Design Studio, for instance, is very widely used for battery manufacturing, battery design. And they were committed in order to deliver, and thanks to the other partners that we had in the project, so material manufacturers, battery manufacturers, there are very special relations between Siemens and them in order to listen to what they were expected from the software, what could be improved before the project, during the project, and how it could be delivered. So it was also part of one of the deliverables that we had in the project to know what was the partner's requirements and what was the partner's expectations for the results. And in the end, we said, okay, are you happy or not with what we did? What you want to change, what you want to improve, and so on. And they still have some access to the softwares until end of this semester in order to test and to learn to use them for further applications.
Very interesting, thank you. Any questions up on that, please?
Thank you. Very interesting to see how the projects came out in the end. Very extensive and maybe a little bit too much for me sometimes. This is Ian Five from Bosch. One of the motivations for the call itself, I think it was about 4 or 5 years ago, right, so this was we didn't have a basis even on the measurement technologies in order to get the data that we needed to build up the models. Would you say that we are better today now? Do we have and especially in a standardized way? In other words, how do we compare the results from one experiment to the other experiment, from one consortium to the other consortium? Is that still sort of an open book here, or are we better now if we? I'm imagining putting both of the projects together on one communication platform so that people can say, okay, that's how they did it. Not looking so much at the details of the models themselves, in the fine details, but really, how is the procedure taking place? What are we doing to do the measurements? Of course, everybody is responsible for their own scientific validity, so to speak, and that aspect. But can you comment on that? Are we better now today? I mean, the results, if I look at it from the bird's eye perspective, it's great. I think it's wonderful. I think we've made a big push here, and especially when you're able to estimate and say, now we're this much faster because that was the idea. But we'd like to make the bridge as to basically how can we influence also the improvements in battery manufacturing, cell manufacturing. That was a lot of questions in one.
Yeah, it's a lot of things that we discussed a lot with Elizabeth yesterday already, and when we meet on this subject, we try to discuss it during the project, and obviously with the COVID and so on, it was complicated to maintain the cohesion within the project. So outside the project, it was even more difficult during this time. What we at least within the project, we try to create common rules for everyone to share the common good practices. There was a lot of things to learn. For swelling of the electrodes, it was something new. How do you measure it? Do you stop the swelling and you measure the stress? Do you put a stress and measure the swelling? It was the first obvious question that we had. So we had to decide a lot of things on that. We developed new things in order to observe the conductivity of solid-state electrolytes with very low TRL. So from one experience to the other, we have a lot of differences. So it was obviously not so straightforward because of that. And we tried also to keep up with the other projects, especially from LCBAT 5, LCBAT 7, to see what was done, what was the difficulties. RTR conferences were very interesting for that, to see what were their state and what needed to be done on this subject to try to get some experiments with that. But yeah, more efforts should have been done, at least from a data point of view, to see what was done and compare with other projects on this.
Yeah, I think you touched a very interesting point, and yeah, because I remember from the call test that it was mentioned that it needs to address something like a reduction of the experimental work divided by 3, something like this. So we thought very much on that. So we think modeling can contribute, but the way you extract the data is crucial, and the method you follow and the standardized way you do the experiments is crucial here. So within the DEFACTO, we thought, okay, we don't have final answer, obviously, but we are setting a basis, and this is what, at the beginning of the project, we had a lot of discussion, which is the best procedure for extract the porosity, which obviously is needed for validation of many models within the DEFACTO. Is it the porosimeter the best way? Should we consider the theoretical value? Exactly the same for the tortuosity. Should I take it from the FIPSEMS pictures? Should I take it from the impedance measurements? So we were very convinced that we needed to somehow standardize, or maybe standardize is a very very broad word, but uniform the protocols. And this was the main idea of setting us this CINEA workshop. So first, identifying which are the best, the parameters that I need for model validation, and then the procedure. Obviously, the fact, I'm not sure, I mean, it's not fair to say we are better now than 5 years ago. only thanks to DEFACTO, because I mean I'm aware that many other European projects are working already on that level. There is already a Battery 2030 Plus community working very much on the standardization and so on. Many other possible Horizon Europe projects as well, but we wanted to, with this idea of reducing the experiments, but also reducing, uniforming the way we measure. This was something we were pretty much convinced in the project, and we come out with something as a baseline, again, I would say.
Can I ask one more question? Okay. Well,
I think we have 5 minutes. If it's a very short question.
0 minutes, but the big question that I have now is what's next? What are the open areas? What haven't we covered here? I'm really very interested in seeing the application in terms of using the models now to develop cells that are good for manufacturing. Would be my sort of top-down, take this approach here. But do you have a list of the to-dos left? That's not too generalized, but really this could be improved, that could be improved. We still have to do a lot of work here.
I mean, at least in the fact that there are a lot of things to do, and on the modeling as well, there are a lot of things to do. So we will need to improve accuracy still, because we are navigating within different chemistries, Gen 3, Gen 4, maybe Gen 5. So there are a lot of things to improve on the calibration, on the accuracy, on the computational cost. So, but then we need to fund it, obviously. And which it would be great to have this again an opportunity. So what I can say is that, but this is now I'm talking about only on behalf of CINEA, is that we are also taking advantage of these kind of models because we have the capability to manufacture prototype cells. So we are very much in contact with the developing team. So because I think this is the way we need to grow, and we need to be competitive, with the surrounding landscape. So more or less, this is our view on the topic.
As was said by Elizabeth, it's just a beginning, because we can use that for other project, for other applications. So we are involved, especially with DEFACTO, in a new project which was accepted last year, where we will be able to use these models in order to create new Gen 4 cells. So it's very interesting to see how we can use these models and what needs to be adjusted compared to what we had in the first steps. If in IFPN, for instance, we have some teams that are developing new materials, so they need to see what are the difficulties with these material challenges in order to implement them, and to say, okay, we are solving this challenge, and by solving this challenge we can improve the performance or not. So these kind of things can be implemented and using these models for these applications. And so that's a lot of things that can be done. In terms of pure modeling, one of the main difficulties that we faced from modelists, for instance, is upscaling for transport properties. When we use transport modeling for NMC, for instance, you want to have that from the crystal and go it to the full particles. It's a very big challenge because the particles are anisotropic. You have a lot of crystals, and the behavior is not the same as a pure crystal. And that's something that was not being possible because we discovered it big inside the project, so we did not have time to go further. It was a huge challenge, and something that's still a challenge at the end of Modelis. But that's something that you see in a lot of publications now, that from crystalline point of view to full cell point of view, there is still a huge gap that can be served by AI and things like that, but needs to be addressed in further developments.
I'm sure there's when you talk about AI, we can go into a lot of details, and a lot of additional questions. I think there's one question on your side. I'm not sure where the microphone is. Maybe to finish it off.
Okay. Thank you very much. Just a question: if these models are more chemistry sensitive or morphology sensitive, what is? So they can be used for different chemistries or different morphologies? What's the main issue?
Yeah, so within the DEFACTO in particular, we were very much focused on the lithium ion and very much on the steps on roll-to-roll application. So, yeah, electrode microstructure level, obviously electrolyte filling, so liquid scale, liquid lithium ion. So it's not only about chemistry dedicated, because you can have, even though you don't have silicon, you will have certain expansion within the lithiation. So the mechanics is always really important, even if you need to think from cell to pack. For instance, if you need to design properly the module or pack, you need to take into consideration any swelling of the cell. So so I would say that in the DEFACTO we were very much focused on the lithium ion, even though, if you respect the physics, it can be used, it's agnostic, I would say. Obviously, it cannot be solved for lithium sulfur directly, because it's completely system and many different mechanisms, processes. So, so we were very much focused on that level.
Yeah, the aim of this physics-based model is to see what are the implications of the different parts of the mechanism that we are witnessing. So obviously when I began the modeling of batteries, we were focusing on electrochemistry, or electricity first, electrostatics, and then electrochemistry. Now we see that mechanics has a huge part to play, especially for lithium plating, for mechanics of the electrodes, for lithium with silicon, with lithium sulfur, and so on. So you need to take more and more mechanisms into account. It's more complicated, but the idea is to say, okay, we have this model that is working. We put this into with specific parameters that are fit for our applications, and now let's see what are the impact of mechanics. Is it negligible or not? Can I say, okay, we can stick with electrochemistry, or do I need to take into account mechanics on my systems? Do I need to take the thermal aspects or not? So am I able to neglect some parts? And the idea is to simplify in order to optimize what is really needed to be optimized for a better behavior. And obviously, if nothing can be optimized, you need to create some compromise between mechanical behavior, electrochemical behavior, electrical behavior, chemical behavior, and so on.
Good, thank you very much. Looking at new cell chemistries to come, I assume there's a lot to do in modeling, Gen 4, etc. You mentioned the topic of swelling, which is a big pain for especially then the integration, I can say, and looking at the measurement, and I fully agree, getting the data from the measurement and how you measure is, I assume, key to then go into modeling. I think we had 5 minutes more, and we used that. So thank you very much. I hope some of the questions were answered. If there are more, I am sure that you two are staying here to answer those. Thank you very much for the discussion.
Many thanks from my side as well to all of you. So for now, the lunch is served downstairs, and please don't hesitate to check the stands as well. You've seen there are several from the Commission, but also from our projects and other partnerships. So please don't hesitate to go and check them as well. Thank you.